Welcome to week 9 of computational quantum chemistry. So up to now, whatever calculations we have done, we were using a single method for the entire system. So today we are going to know about multi-layer modeling, where you treat different layer of the system at a different level of theory depending upon how important are they for the chemistry involved. So, when we think of what kind of method should be used depending upon at what length scale the phenomena is happening. So, for the length scale femtosecond to picosecond, you are supposed to need very high accuracy and you need to use the quantum mechanics. But the problem is that with the quantum mechanical methods, they are very expensive. So, it is very difficult to perform it beyond 10, 15, 20, 30 atoms depending upon what kind of methods you are using and what kind of computational facilities you have. If you consider the semi-empirical methods to be quantum, they can be considered as quantum because finally they are solving Schrodinger equation, only your Hamiltonian are parameterized. So, they are not ab initio, but they are still quantum. You can go up to, let us say 100 atoms. When I say 100 atoms, means you can do geometry optimization, probably a small scale dynamics with that. So, 100 atom will be the limiting case for most of the systems unless you have a entire supercomputer dedicated for yourself, which is very often is not the case. Now, if you want to go from picosecond to a microsecond phenomena, a good idea is to use molecular mechanics. And molecular mechanics, you can have atoms like 10 to the power 4, 10 to the power 5 atoms at the max. Depending upon, of course, which kind of force field you are using, you are having GPUs or not. But both the electronic structure and up to 10 to the power 5 atoms, you are still looking at the molecular level phenomena. So, if you go to millisecond level phenomenon and if you go to atoms which are more than 10 to the power 5, then basically mostly you are looking like assembly like phenomena. So, you need to use some kind of a coarse grain methods. This is very difficult to do even with the standard molecular mechanics. So, for most of the purposes in this course, we are going to use the multi-layer modeling, where the chemical important part we are going to treat in a quantum mechanical level, and the less important part, which maybe act as a background for the reaction, that we will treat either in a molecular mechanics or some cases in a semi-empirical method. Remember, although the main reaction happens in the quantum region, the background, the environment which actually acts, is actually very important for the happening of the reactions. So, nature can perform reactions very efficiently because it has come with a proper 3-dimensional arrangement through millions years of evolution, which is very difficult to mimic without that particular arrangement of the environment. So, it is essential to use multi-layer modeling, and multi-layer modeling has various applications. You can treat solid state using that. You can see biological phenomena, drug discovery, molecular like QMM methods plays a major role, where you try to understand small molecules binding to proteins. These small molecules actually acts as drugs, and people try to develop very accurate method which can predict this kind of models, this kind of phenomenon with near experimental accuracy. Now, so we have discussed about the quantum mechanical part. We have seen how Schrodinger equations can be solved, various approximation involved, what kind of basis set, how to reduce computational cost, how to find out transition state, all other things. Now we are going to know a little bit about molecular mechanics. So, this is a representation, schematic representation, where you treat different parts of the molecular mechanics force fields. So, molecular mechanics is a computational method that computes the potential energy surface for a particular arrangement of atom using potential functions that are derived from classical physics. So, these are completely classical, they are follows the laws of classical mechanics, but they are often derived, they are often fitted to quantum mechanically calculated properties. We will come into details what do I mean to that. So, molecular mechanics ignores the electronic structure and calculate the potential energy of a system in a function of nuclear positions only, and the potential can be separated into a bonded and non-bonded part, where the bonded part will have, of course, the bonds, the dihedral and the torsion, and the non-bonded part is the second line, where you have the Coulomb kind of interaction between the atoms, and there is a Lennard-Jones potential. Remember, Coulomb interaction is a classical interaction, although it has charge involved, it's actually a classical. way of describing interaction between two charged particles. Now, here in this equation, Nmm is the number of atoms in the system, bond angles and bonds are described using the potential modeled by harmonic functions and torsions by periodic function. We are going to come into more details of it, and the pairwise interaction between the atoms with a partial charge are described by the classical Coulomb law, where Rij is the atomic distance. Now, we will go to the terms one by one and try to understand how the individual form of the potentials looks like. So, in most of the cases, we consider that bonds are like springs. So, if you stretch the spring, it will behave like a Hooke's law. Now, first thing is the bond stretching energy. So, E stretch is the energy function for stretching of a bond between two atoms type A and B. In its simplest form, it can be written as a Taylor series expansion around a natural or equilibrium bond length R0, and if I terminate the series at the second order, this is how it will look like. Of course, if I doing the Taylor series expansion near the equilibrium bond length, remember my gradient will be 0. So, d by dr, so my second term will be 0. So, I will be left with E0 and the first term, and this is essentially like an harmonic approximation. So, here what is called P2. So, if you see the black solid line is the exact, and the P2 is actually essentially will give you this line. So, this line is quite good around the equilibrium bond length, but because it is a harmonic potential, when I am stretching the bond, this is not so great. So, the harmonic form is simplest possible and sufficient for determining most equilibrium geometries. You can see it here, but there are certain strained or crowded systems where the result from an harmonic approximation is significantly different from the experimental values. And of course, if the force field should be able to reproduce features such as vibrational frequency, functional form of E stretching must be improved. The straightforward way, of course, is to contain more and more terms. So, if I take up to fourth order term, still my stretching behavior, it's improved a little bit. If I compare to the solid line, this is the solid line. So, this is P2, where up to second order derivatives I have taken in the Taylor series. If I take up to fourth order, of course, it improves away from the equilibrium a little bit, but it still cannot accurately reproduce the behavior. So, the most easiest way to take a Morse potential, which has the following form, an exponential form, and Morse potential generally gives a good agreement even at the stretch geometry, much better what you get from including fourth order term in the Taylor series expansion. Now, the bending energy is required for bending an angle formed by three atoms A, B, C, where a bond between A and B there is a bond between A and B and C, and similar to E stretching, bending is usually expanded as a Taylor series around a natural bond angle, which is the equilibrium bond angle, and terminated at second order, giving the harmonic approximation. So, this is how it looks like. Here you see the harmonic approximation generally gives a pretty good agreement, at least near the equilibrium. While the cyclic harmonic approximation is adequate for the most application, there may be cases where the higher accuracy is required, and the next improvement will be to include a third order term analogous to E stretching. And if I go to this third order term, they generally gives a good description over a large range of bond angles. Even away from the natural bond angle, they are generally good. Now, the third important thing is the torsional energy. So, the torsional energy is fundamentally different from E stretching and E bending in three aspects. The first one is that a rotational barrier has contribution both from non-bonded as well as torsional energy. So, the torsional parameters are therefore coupled to the non-bonded parameter. In case of stretching and bending, it only depends upon the stretching mode or a bending mode. It does not have any coupling with the non-bonded, but this will not be the case with the case of torsional. So, the torsional energy function must be periodic in the angle. So, if the bond is rotated at 360, the energy should return to the same value, which is also different from what we have seen from stretching and bending. And third thing is that the cost in energy for distorting a molecule by rotation around a bond is often low, and that is a large deviation from the minimum energy structure may occur in a Taylor series expansion in omega is therefore not a good idea, because the energy values are so small that by taking the derivative it may not be converge into an harmonic kind of approximation. So, you need to take more higher and higher order of derivative. So, good idea is to express the T torsion as a Fourier series, where the value of the n depends upon what kind of rotation it's describing. So, if n is equal to 1, the term describes a rotation that is periodic by 360 degree, and n is equal to 2 is periodic by 180 degree, n is equal to 3 is periodic by 120 degree, and so on. So, the combination of these terms will give you the final form of the rotation around this B bond. So, this is the dihedral connecting A, B, C and D. So, this is for n is equal to 1. You can see that the potential returns at 360 degree to the original form. This is the for n is equal to 2, where it is periodic at 180 degree. So, it returns to the original form at 180, and this is for n is equal to 3, where it returns to the original form at 120 degree. So, if I combine them, all three of them, I get the resultant form of the potential. If you look it very carefully, so you can see that at 180 degree, this is how where the minima is. So, this is reproduced, but and also around the 60 degree there is a lowering of the thing, because this gets added to this one. So, and of course, remember at 60 degree this is slightly lower. So, if I combine, it is slightly higher at 60 degree, this one is quite high. So, if I combine this one with this one, this is where I will get the thing. In case of 120 degree, this one is lower and this one is higher. So, if I take a combination, this will how the potential looks like. So, this is the overall form of the potential, how it will look like in the case of a torsion for dihedrals. Now, of course, in addition to that, I need to take the van der Waals interaction. We have talked about van der Waals interaction. These are the weak interactions, dispersions during describing the D corrections to DFT. So, the van der Waals interaction, for example, the combination of short range Pauli repulsion and long range dispersion attractions are most often modeled by Lennard-Jones potential. In case of DFT, the advantage was that the small short range Pauli repulsions were automatically taken care by basically the DFT functionals. So, what was missing is the long range dispersion attractions, which we were adding by some kind of a potential. Remember, in case of a wave function based method, this is not a problem, where both the short range repulsion and the long range dispersion are automatically taken care by the wave functions. So, this is the functional form where this r to the power 6 dependent term is actually an attraction parameter, which is like a long range dispersion, and c to the power 12 parameter depends upon a repulsion parameter, which depends upon the atom type I and J. So, this is the Lennard-Jones form of the potential. You can have different other form of the potential also, Buckingham potential, like many other forms are possible. Electrons are thus ignored by the molecular mechanics force field, and their influence, of course, we know that the electrons, if I think of the electron as a classical thing, they are like charged particle, and their influence is expressed by an empirical parameter that are valid for the ground state of a given covalent structure. Therefore, the process that involves electronic rearrangement such as chemical reaction cannot be described at level. Instead, the process requires a quantum mechanical description of the electronic degrees of freedom. So, molecular mechanics can describe multiple things. It can describe structure, vibration, other things, but not actually chemical reactions, because chemical reactions involve electrons and electrons are quantum mechanical particle. So, depending upon what kind of individual values of stretching, bending, distortion, the van der Waals parameters as well as the point charge are taken, you can have different kind of force field. These are the list of the popular force field which is generally used, and this is actually a very restrictive list. I am no longer claiming that this is a full list, but at least I have tried to incorporate most of the popular force field. You have AMBER, which is full form is Assistant Model Building and Energy Refinement, CHARM, Chemistry at Harvard Molecular Mechanics, GROMOS, Groningen Molecular Simulation Package, OPLS, Optimized Potential for Liquid Simulations, CPF, Consistent Force Field, COMPASS, Condensed Phase, Optimized Molecular Potential for Atomistic Simulation Studies, MFF, Mark Molecular Force Field, and many of them. Even I will not remember the full form of all the force field, and I believe I do not remember any of it. I just remember the acronym AMBER, CHARM, GROMOS, OPLS, CFF, and different kind of force fields are parameterized for different kind of systems. So, the force fields can be available, the same force field can be applicable for all kind of systems, but some force fields are better for certain kind of systems, like charm is better for generally considers for proteins, amber is for nucleic acid, and these force fields are in the constant state of development. In many of the cases, so there is a standard recipe how to parameterize this force field, and in many cases for some non-standard small molecules this force field will not be available. In that case you have to parameterize yourself. We are in this course we are not going to show you how to parameterize force field yourself, because this is simply outside the scope of the present course, but there are a lot of literature available in the internet. Especially VMD offers a very easy guide how to use how to parameterize different force field using quantum mechanical calculation. And this is what I was discussing. Although the force field does not have any quantum mechanical parameters itself, it is a classical mechanic, it is governed by classical mechanics, but the parameters which are optimized often to quantum mechanically calculated values, quantum mechanical bond length, quantum mechanical angles, distortion energies, the interaction parameters, interaction energies, point charge. So, these are calculated by quantum mechanics, and then you fit your force field to that, and there are detailed scheme available how to do that. You should search on the internet to find more about it. Now, to describe about the ORCA although ORCA, it's possible to run ORCA QMMM calculation or ORCA MM calculation using various third party software, like I know Amber has a interface to the ORCA which is well maintained. NAMD has a very nice interface to the ORCA which is also well maintained. GROMACS, I believe it's possible to do GROMACS QMM calculation using ORCA, and many force fields can actually do calculations using ORCA. But ORCA also has an inbuilt MM module which allows you to do MM or QMM calculation by using standalone ORCA. For the MM part of the ORCA MM calculation, force field parameters are necessary, and ORCA has its own parameter format, and that is called ORCA FF-PRMS, which includes atom specific parameters for non-bonded interaction. And the easiest way to generate the ORCA PRM file is to convert it from a PSF file, that is a protein structure files, which is generally a NAMD file. So, PSF files are basically for to a CHAM force field and its application via NAMD. PSF file for a specific proteins can be easily generated by popular molecular visualization software VMD and its extension QuickMD, but also with other extensions of the VMD program like PSFGen or FFTK. We are not going to go into the individual value of it. You can search the VMD website. There are a lot of tutorials available there how to generate these PSF files. And the PSF files contains information of the atom types on bonded interaction of all atoms. It does, however, does not contain the parameters. So, it only says what kind of interactions are there, and the parameters actually written in a different file. And we are going to look at the parameter files also. So, these parameter files are generally has an extension or PAR or STR, and the CHAM parameter file comes with the VMD installation and they can be directly downloaded. So, the things what you see in the blue actually has the so it has an embedded URL link. So, if you click them, it will take you from the place where it can be downloaded, or it can be generated using the VMD extension FFTK, that is the force field toolkit. Now we are ready to perform our first ORCA MM calculations. The file required will be so this is a system thymine surrounded by 10 water molecules, and this is one of my favorite system. So, thymine is actually a DNA nucleobase. DNA nucleobase is a part of the DNAs what we have, which contains our genetic secret. So, DNA has 3 parts, which is a nucleobase. There will be a sugar and there is a phosphate. So, nucleobases are hydrophobic, and you know the double helix structure, the nucleobases are put inside. So, nucleobases are of course not the actual DNA, but this generally gives you a very good model system, and we know that in the presence of radiation the DNA undergoes damages. So, if you want to simulate those damages, it is generally a good idea to start with a very simple model system, and then you can try to understand what is going on. Of course, in the body the DNAs are surrounded by water. So, you can take a few water molecules to model this one. So, this is a system where it contains thymine and surrounded by 10 water molecules. To simulate that, what you need is that the geometry in the PDB file, the thiamine water PSF file, which is the charm compatible force field, which tells which kind of interactions are taken, their individual value will be taken in this par underscore thiamine dot 2 par. This is PDB file, dot PDB is a PDB file, dot PSF is a PSF file, and par thiamine dot 2 dot par is actually the parameter file. And this contains the thiamine parameter. For the interaction parameter for the water is contains in the top of par water ions underscore namely dot str. So we told that the parameter file can be both dot par or dot str. So you can download all of this from this link. So if you go to this link, you will find all these files and you can download it. So in my case, I have already downloaded them. So I have all the files. So let us see this file one by one. So first let us see the thiamine.psf. Okay, let us see the PDB file first. So PDB is a protein database file format, and let me open it with first with Chemcraft to see how it will look like and how you can see in the Chemcraft different things. So Chemcraft, the advantage is that if you open the PDB file, you will see each of the constituent, each of the fragments individually. Now you can select one of the fragment and you can say that okay, show only atoms for the chosen subunit. So what it will do is that you will not show the water, you can only see the thiamine. So sometime what happens in a very big system, it will be, if you see the entire system, you will not able to make any sense out of it. So it's a good idea to just see one fragment what you are interested at and then modify there, or put that fragment in the QM level like that, or optimize that fragment. So for this kind of thing, this is generally a good idea. You can, if you want to see what the file actually looks like, let me open with Notepad. So this L is for ligand, and it shows that these are actually the main atoms, the main fragments, and these are heteroatoms. So these are actually the solvent molecules, and this ends with the end statement. You can search in the internet if you want to have a detailed discussion of the PDB file. Now thiamine water.psf, this I can also open in the Notepad. So this actually says what kind of interactions are there. So first of all, in the first part, what it gives is the corresponding mass and the corresponding point charges. So these are the corresponding point charges. In case of water, it will be very simple. So you see that. So in the case of thiamine, will be treated using an FFTK generated charm compatible force field, and the water will be taken by tip 3 model, which is a rigid water model. So the geometry will not change during the optimization, and you see that the oxygen has a point charge of 0.83 and this one has a point charge of 0.41741. So each water molecule will be neutral, because if I add them together, I will get plus 0.8340 and this is minus. So each water molecule will be neutral. So this is the non-bonded parameters, the point charges. Then it describes which of the atoms are bonded, like 1 and 2 and is bonded, 1 and 3 is bonded, like this it goes on. It describes what are the angles. See here, it is only given which is bonded to what and what is the angle. The values of the bond length, the parameters for the bond length, bond angle or dihedrals are not given here, and it gives you the description of the non-bonded interactions also. So the moment I go to the .par file, I will give the individual force field parameters. So this is for the thiamine. So it says how it is described. So bonds are described by a harmonic potential, angles are also harmonic potential, dihedral is actually given by a Fourier series, and the corresponding epsilon values are given here, and this is how the Lennard-Jones potential is described by an r to the power 12 term and r to the power 6 term, and the point charges were already given in the PSF file. So, this is how the file will look like. Now, to perform the calculation, what I need to do, first I have to generate the Orca PMS file, and this is the keyword to generate the Orca PRM files. So, I have all the files here. So, what I will do here, I will open terminal, I will again use MobaXterm here. So, I will copy the thing. So, this is my force field parameters got generated. Maybe I will rename this one. As what dot water dot orca ff. I'll see what I will show you what is there inside. Now let us open it.